Recording.
Okay, so it's a pleasure to present Victor Hernandez Santamaria from Facultad de Ciencias UNAM. Victor did his PhD under my supervision at Investaff. So he came from engineering, but now he's a very strong mathematician and he forgot everything about engineering. No, I don't know. No, he knows a lot of engineering and mathematics. So it's really a pleasure to have him here. So he's going to talk about from forward noise to backward stochastic PDEs. So please, Victor.
Yeah, thank you, Cero, and thank you, Juan, Johnny, all of the organizers for this very nice seminar. And yes, I prepared this talk based from a perspective that I would like to share about what I know about stochastic differential equations and what I have done in this direction. So this is the goal of this talk. Okay, so it is based, or the last part of this talk is based on a joint work that I have with Camille Levat from Sorbonne Université and Liliana Peralta, also from here, from Facultad de Ciencias at UNAM. And the first thing that I would like to present to you, or to give you an idea of what it is about, it's what is a stochastic differential equation. All right. So to fix ideas, let me start with a very basic equation. Okay. So let's consider the ordinary differential equation that I think, or that I use as a model of population growth. Okay. So here n is the unknown. It represents the size of the population at time t. So given an initial condition and a growth rate, what I'm interested is in how this equation evolves in time, the dynamics of this equation. So for instance, if you think that C0, it's a constant, you fix it, you fix an initial datum, and you think that this is a positive constant, the solution grows exponentially. This is the classical ordinary differential equation. And given an initial datum at time 0 here, this equation evolves. And you can know exactly the solution of this equation. You know the evolution of this equation. And every time you run this experiment, you will obtain exactly the same result. So this is what is called a deterministic model. Once you fix the growth rate C0 and the initial datum, there is only one possible trajectory or outcome of this evolution system. All right. But this is too perfect to be realistic in nature, in real life. We know that this cannot be possible. If we start some experiment, it is known that it is always perturbed by some noise, by something, external forces that influence how this model behavior, sorry. So one may think that some random forces affect the model parameters. For instance, in my population growth model, C0, which was the growth rate, we can think that this parameter is affected by some random noise. Okay, I will make precise later the sense of the noise. But think, for instance, in this, if this represents an ecological model, the weather can change the reproduction rate of the population that I'm modeling. All right. So instead of having C0t, a known quantity, I have some CT, a nominal quantity, plus some random noise that I call it here he, and a parameter A that it is called the noise intensity, how strong or weak this noise is affecting the dynamics. All right. So if you just replace this parameter into the model, you end up with a differential equation that looks a lot or resembles a lot the differential equation that you had before, this part that we know that it has a deterministic behavior, plus now there is the unknown quantity multiplied by this noise. So here I'm depicting some the behavior of this equation, of this differential equation under this noise that I want to make precise. So instead of having the blue line that it is here, that it is the nominal or the deterministic response of the system, I can have different trajectories depending on how the noise is affecting, okay? And the state, the solution is no longer deterministic, and the trajectory becomes a random process. It becomes a random object that depends on how this this random force enters the system, okay? So this is, let's say, a basic motivation, but what is exactly the noise, okay? So in practice, the noise, we would like for it to model some small, independent, and rapidly fluctuating effects, okay? So how a small perturbation affects the parameters in the model. So this has been studied by physicists, especially, and there is some stochastic processes that is called white noise, that it is a idealized model for random fluctuations with no temporal correlation. So it's how it's strong or quick perturbation in a very small amount of time with high intensity. So this is a phenomena that has been observed by physicists, but also mathematicians have been interested in this. And one representation, or a very convenient representation of this white noise, that it is this process here that I put in the previous slide, that it is affecting my system, it is the derivative of, or the time derivative of the Brownian motion. But I would make some comments about this. This derivative, this equality that appears here, should be understood in the sense of generalized stochastic processes. What I mean is that if you come from a PDE background, you know that there exists this notion of weak derivative. So this white noise, this process heat that was affecting my previous model, should be understood as the weak derivative of this Brownian motion. So why is this this notion, or why we should study this white noise as this weak derivative of the Brownian motion? And it is because if you remember your courses on stochastic processes, the Brownian motion has a very nice property that it is everywhere continuous, but it is nowhere differentiable. So we cannot differentiate it in the classical sense. But in any case, this Brownian motion, here I'm presenting a picture with different paths of the Brownian motion. It has good properties. It models the rapidly fluctuating, non-correlated random processes that I was just saying. But it also has some other good model properties. For instance, it has zero mean, that all the possible trajectories, when you take the average over all of them, this average is equal to 0. And also it has independent increments. That means that if you want to study how a small step in the evolution of this Brownian motion, this step, this small increment, is independent of all the previous history that has passed in the evolution of this process. So if you write the equation in an integral form, the first equation that I just had, that I wrote it here, dt n of t equal to c0 t and t plus it was a and t dt. If you integrate this in time, and you end up with this expression. And one of the difficulties of studying this differential equation is how to study this integral, all right? So this key, which is the weak derivative of this stochastic process, it is not integrable in the usual sense. You cannot use your usual calculus tools to study this integral. But this was studied many years by Kiyoshi Ito, where he developed some theory to replace this object that it is there, and to give a meaning of this integral in terms of this stochastic process, okay? So you can think about this integral in this model as a generalization of the classical Lebesgue-Stieltjes integral. Okay, it loses many properties, but in any case, you can develop theory to resemble the tools of calculus that you know, and with that you can study differential equations. A convenient differential notation, and that will appear in several places in my presentation, is this one, where again you can recognize the classical structure of the differential equation that I want to study, plus some extra term, the so-called additive multiplicative noise, that it is written in terms of the Brownian motion and the unknown variable. Okay, so how we should think about a stochastic model? So let me give you some ideas or some intuition of how we should think about the solution, this model, etc. Okay, so for each realization of the Brownian motion, for each path that I show you, you can have as many paths as there is in your probability space. The equation produces one trajectory. This was exactly the drawing that I was showing before. So for each realization of the noise, I can draw some trajectory of the evolution of my system. All right. So the solution is not a single curve. It is instead a family of random trajectories. The solution is just this complete family of random trajectories. As it is written here, different realizations of the noise leads to different trajectories. But the most important thing is that the evolution of each trajectory depends on how the noise evolves. It depends on how it is being driven by this Brownian motion. Okay, so one important thing about these models, and this will connect later with the work that I want to present, is that since the noise evolves in time, the trajectory, every path that I can draw for the evolution of my equation, it's reversed step by step, and this is related to the independent increments of the Brownian motion. What I mean is that at time t, when we see the trajectory of the evolution of the system, we only know what has happened before. We don't know any information about the future, because as I wrote before, the increments, the small increment in the future, t plus h, it's independent of all the past trajectory of the Brownian motion. So the collection of all the information that I have gathered from my experiment, it is what is called a filtration, okay? And we denote it by f of t. So this concentrates all the information that has been generated by the trajectory of my problem, and in particularly, because it is being driven by a Brownian motion, it is a collection of information gathered from the evolution of this Brownian motion. In our example, and you can think it also in terms of analysis, this filtration is the sigma algebra, or the minimum sigma algebra generated by the trajectories of the Brownian motion until time t. So this time is the same that has passed where I have observed my experiment. Of course, as time increases, the filtration contains more information. Okay, so this is just a way to say that the trajectories generate some information, but what I know is only what has happened until the time that I'm observing the experiment. Okay, so this is actually, this part is the one that connects with the title of my talk. Stochastic differential equations are used to model things, model the perturbation of a phenomena when noise is affecting it. Okay, but what I'm interested in is in another kind of differential equation, stochastic differential equations that are known as backward. Okay, but this also has some modeling some modeling intuition that I want to show you in these slides. Okay, so let's come back to our stochastic differential equation that now we know how to interpret it, how it evolves in time. And suppose that we're interested in the following. We define this variable he, and which is different from the white noise that it was before. I didn't notice that I used the same variable. But he is a function g. It doesn't matter for now what is the function, but it is evaluated at the solution at time t. Okay, so I'm interested in how this number is, or what is the behavior of this number when I evaluate the function at the solution at time t. Of course, since this is a random process, he is also going to be a random variable. I don't know a priori the value of this function, and it depends on what the trajectory of this of the solution of this stochastic differential equation. Of course, if I wait until time t, if I study this phenomena at time t, I will know for sure the value of this quantity here. All right, but at any other time t is strictly less than t, the value is not known for me. Why is that? Because, as I said, this equation evolves in time, evolves randomly, and I don't know how is the information going to be at the end of the experiment. Okay, but in any case, many people have been interested in this kind of questions, particularly people in financial sciences, economics, because it can model. If you have seen these graphics from the trade markets, you can resemble this kind of same trajectories. Okay, so these quantities, how to evaluate these quantities, it is interesting for those people. All right, so not everything is lost. Why is that? Because at time t, extremely less than t, we have access to the information of t, the filtration that I have been generated with the solution of my equation. Okay, so what people have realized is that a natural way to describe this evolution is to by giving the best estimate possible given the available information. In terms of probability theory, the process yt that it is here, that it is the conditional expectation of the variable here that I want to study, given the filtration up to time t, gives the best estimate for this random variable. Okay. In terms of, let's say, of analysis, you can think of as the orthogonal projection of the unknown the value phi that I want to study into the space of the f of t adapted measurable random variables. Okay, so this y of t is giving me the best estimate possible of the unknown quantity. Remember that this is up to time t, capital T, given the available information, the iteration that I have been generated of until time t less than t. Okay, of course, at time t, if you evaluate this conditional expectation, you recover exactly the value, which coincides with the intuition that I showed you before, that if we wait until time t, we will for sure know the value of the experiment. So from a differential equation point of view, which is the one that I'm interested, the question that arises naturally is, can I say something about the evolution, how this quantity evolves as t evolves? And the answer is yes, we can write a differential equation. And for that, let me show you two cases. The deterministic case, when there is no randomness, for sure we know what is the value of the solution at time t. This implies that there is no new information coming from any random process. And if you just differentiate, you will see that this satisfies a differential equation with a terminal condition in terms of this data here, and that evolves backwardly. We know what is at the very end of the experiment, and we propagate the information backwards. Okay, so in the stochastic case, as I said, new information arrives through the evolution of the Brownian motion. What you can prove and what it is known is that this y of t is what it is called in probability a martingale, and you have very nice properties for this process. In particular, you have a theorem that is called the martingale representation theorem that says that that quantity that it is evolving in time, it can be written in terms, or it exists some extra process C, such that the evolution, or such that this quantity evaluated at time t is what you know, plus or less some quantity that you need to subtract, and that it is evolving also with the Brownian motion. Okay, if you do more or less the same trick that I did here, what you end up is with a or you end up with a stochastic differential equation with a terminal condition, but that has some extra term. You see here we have 0, here we have the zeta t that comes from some representation theorem. Okay, so in general, backward differential equations arise from this point of view. We have some quantity that we want to evaluate, plus in this other example, I added some extra term h, but that I want the best approximation of this quantity in terms of the information generated until time t. In this case, the differential equation that models or that governs this evolution backwards in time, it's again an equation with final datum and some extra terms in here. In general, what it is a backward stochastic differential equation, and this is the one that I would like to show later with my work, is it's an equation, a stochastic differential equation, where we have a terminal condition, where we have a noise term in the same sense as the forward term, that it is some term depending on the Brownian motion, and some, you can think, possibly nonlinear function depending on the unknown y, and this also other unknown zeta. But there is a very important difference in between the usual stochastic differential equations that I showed you before that came from modeling, came from random perturbation of some models, and is that this noise, zeta t, does not represent any external noise. What it describes, it's how the prediction that I want to impose of a future quantity evolves and adapts to the information given by the trajectory of this stochastic process. In particular, also in the backward equations, there are two unknowns. One is the random process C, and the other one is the random process Y. One accounts for how the evolution is, or how the evolution is done, and the other how it adjusts to the noise or to the filtration generated by the Brownian motion. And you can think, if you know or you come from an optimal control community, you will recognize that these equations that have terminal conditions that evolve backward in time appear in the theory of stochastic control. So all of these examples and all of this motivation that I have shown disappear from works from Bismuth in stochastic control in the 1970s, but he didn't mention any work on backward stochastic differential equation. It was until many years after that people realized that or developed a theory specifically for this kind of equation. But the first appearance of this kind of models appeared from very early 70s, right? So, of course, all the things that I have shown you, it's in the, for a scalar process, an ordinary differential equation. But one would like to do or to study more difficult models, for instance, quantities that live in a random field that depend on two variables, time and space, how this quantity diffuses. And for instance, one can think of a diffusion model given by the heat equation plus some nonlinear terms plus some noise. This will lead you to the same question that I have shown you. How can I study quantities depending on the evolution until time t, and how this future quantity evolves given the information of the noise? And you can think, and this is what we have done in this work, is you can think on backward stochastic partial differential equations. So you have a heat operator with some nonlinear terms and some noise that comes from the evolution backwardly in time of this final datum, and that you can think exactly all of the things that I have said have an analogous in this case. All right. So the question that arises here, and the first thing that one from one that study partial differential equations is, what is the things that beyond modeling? What can we know beyond modeling? So even if backward equation appears through finance, through modeling, to this kind of sciences, when we have the PDE form where we have this exactly thing, from an analyst point of view, one would like to study basic analytical questions for this model. What is the notion of the solution? Does it exist? And does it have uniqueness? What kind of regularity this solution has? And this same point of view was the starting point for the developments for backward ordinary stochastic differential equation. People know from the control theory, from Bismuth, for all of this work, that the backward differential equation makes sense. But when you study the backward differential equation on its own right, then Pardue and Peng, Nicole El-Karawi, Peng, Neste, Philippe Briand, Jingwu, Pardue, many people have studied ordinary backward differential equations from the point of view of existence, uniqueness, classical questions from the analytical point of view. Okay, so for backward stochastic partial differential equations, we have exactly the same questions, but here it is a little bit different, since as you know from PDEs, we have different notions of solutions. Okay, so in this theory, especially for backward stochastic PDEs, several frameworks coexist. You have strong solutions that have all the derivatives that you can evaluate pointwisely. Exactly the same kind of notion for classical PDEs have been studied by Hume and Young, Du and Tang. You have the weak solution framework, Sobolev framework, variational framework, that have been also studied by Du, Tang, and Sang, and middle solution using semi-group theory, and all the analytical tools that you will use depend on how you choose, or where do you want to find the solution for your problem. And if you can see, the development of the solutions or all the theory for this kind of equation is very recent. You can go back to works in 2002. So they are very recent compared to other developments in the PDE theory. Okay, so our motivation for this work with Kevin and with Liliana was to work in a weak framework. I will explain later why, in bounded domains. And our main interest was to improve, or was to study the regularity of the solution, but from the point of view of integrability in the probability variable. As I said, this is a random process. It depends on how you write your probability space, where do you look for your solution. In particular, we would like to know how this behaves with respect to this probability stuff. And the main reason for doing that is because we wanted to study semilinear equations in the case where we can weaken the usual notion of global ellipses regularity that appears in many, not in all, but in many of the previous work that I have shown. Okay, so for that, let me start presenting a linear backward heat equation, which was our starting point. Okay, so if we translate all the framework that I have shown you to a bounded domain and to the backward setting, the backward heat equation looks like this. We have some heat operators, some terms, some linear terms, depending on the unknown variables, y and z, some external noise on a bounded domain D, okay? With boundary condition, the usual stuff, and with random terminal data. Here, I'm going to assume that alpha and B are stochastic processes that are essentially bounded, okay? The important part in this frame is that the notion of weak solution that you know that you know in the classical setting can be written also for the backward stochastic heat equation. It can be written through this product in L2 integration by parts. And what you only need to add, okay, you need to add several things, but the most important part, or the most important thing that you need to remember is that you need to take into account these two extra terms that come from the integration in the stochastic sense, from the martingale representation theorem, but you can recognize very quickly the weak solution or the notion of weak solution for classical heat equations, okay? In the classical L2 theory, we have a result that says that if the final datum is in L2, the source term is in L2, and we take some extra integrability condition, and this is the one that I'm interested in the omega, in the random variables, in the space of random, the random processes, then you can have a unique weak solution that satisfies mostly the the classical energy estimate, except for this term. You have to add this new term. But if you see, it resembles a lot the classical studies of the heat equation in the weak sense, the one that you can find, for instance, in the book of Evans. All right. So the question that motivated us in our work is, can we go beyond L2? Because L2 is very good, it's very nice to do as a starting framework, but in the case or for the problem that we want to study, we needed something more. In particular, we needed to study better regularity for the solution, for instance, LP spaces, but also better estimates in the moments of the random variables. This is, as it is written here, a random variable. It depends on the events that are in the probability space. And increasing this to P gives a better estimates on the moments of the random variables that they are here. So the question, and this is the goal that or the initial question that we started, is if we put LP initial final data, in this case, and LP source terms, can we have these LP moments on the solution of our equation? This was the basic question that that was the starting point for us, right? So previous works were known in the LP setting. We were not the first one to study this. In particular, these two works by Hume and Young, where they studied the strong solutions in dimension 1 in the whole space, or this by Du, Q, and Tang, where they study LP theory, again in RN, the full space, but using best of spaces and harmonic analysis, which differ too many from the weak theory that we wanted. And before our work, the situation in bounded domain was not so clear. Actually, in the paper by Du, Q, and Tang, we could find this open problem that says, to the best of our knowledge, when p is different than 2, the corresponding LP theory for backward expediting domain is still blank. And this was in 2013, and for those 12 years, there was no answer to this question. Okay, so this was our second motivation to study this kind of problem. Okay, so let me show you, and just to finish my talk, to give you our main result and some very basic idea of what we have done. Okay, so our main result in this paper that was very recently published, it says exactly the same, or we answer the question that I have shown you. If you start your equation with final datum in LP, but look that it has now LP integrability in omega in the random space, and if it's also an LP stochastic process, then you have an LP solution. This is basically what our theorem says. You have an LP solution in the variable y, and you have an LP regularity also in the correction term that appears in from the noise prediction. Okay, so if you compare, and this is basically a comparison with the previous result, the fairest comparison is with the paper of Hume and Young. They have done everything in R, in one dimension, whole domain. We have done in bounded domains with suitable regularity. They have used strong solutions. The solutions can be evaluated point-wisely in space and time. We have used the notion of weak solution, where we debilitate many of these first assumptions on the solution. And the most important part, and I think this is the main difference with the previous work, is that in the work of Hume and Young, they need a spatial regularity for the final datum and the source term f. What they need is that they need to be differentiable in the space variable, while us, everything fits into the LP space. We don't have, or we don't need any extra regularity to obtain LP solutions. The end, or the thing that you can think of for the story is that LP data gives LP solutions. Okay, so why are LP estimates difficult to obtain? Well, one reason is that if you want to study not just LP, but just L2 energy estimates for the weak solutions of the heat equation, what you need to study is the differentiability of this map that maps T to the L2 norm of the solution evaluated at time T. If you differentiate, you do integration by parts, you will end for sure with an energy estimate in the classical sense. But for stochastic equations, this is no longer possible because I said the random motion is not differentiable, the trajectory is not differentiable in the usual sense. So you need to use other tools. One tool is Ito's formula, which says that for stochastic differential equations, you can evaluate the composition of some function phi, good function, with the solution of this equation, and you can still find some kind of chain rule. This is exactly the chain rule with some extra term that appears in the stochastic setting. Hume and Young, what they did is, since the solution is strong, they can evaluate point-wisely. This is just a number. This is just a number that depends on time. They can use classical Ito formula, differentiate, and obtain the result. In our case, this was no longer possible. Why is that? Because this cannot be evaluated in time, in point-wisely in time, and even if we start from L2 solutions, there is no guarantee that the LP norm of this object is well defined. So all of our analysis, and I will go just to our main result because I seen that I have run out of time, is that what we have proved, and this is the main core of our result, we have proved an LP Ito formula for this finite dimensional problem where we really don't have how a way to evaluate that solution point wisely that works for L2 weak solutions, and to propagate the information of the LP data to the solution. And this formula that I have shown you here is the analogous of the Ito formula in the ordinary differential case, but adapted to a weak framework. And this is the one of the crucial part that was missing from this literature that was pointed out by Kai Lu. Okay, so with this formula at hand, we can do many things now related to the existence, uniqueness, similar equations, even control theory for this kind of equations. So I'm very sorry to go through that part very quickly, but I would like to stop here and thank you for your attention.
Thank you very much, Victor. Thanks for your nice talk. As I tell you before, I have to leave, but we open the microphone for questions. I have only one small question.
Yes.
A term, the correction term is in L2, something like that. So you have some estimation in LP and a correction term in L2.
Yes, let me show you where it is. This one, right?
Yes. No, but
yes, the correction term.
The LP estimate.
The LP estimate?
Mistake or it is?
No, this is the correct way. Actually, this is a very hard question. We wanted to have here P and here P, and we don't know how to obtain this. We really struggle. This is the best that we can obtain. The form of this estimate is inspired from the ordinary differential equation, where they obtained exactly this.
Okay.
I don't know, maybe there's a way to obtain something better, but this is, for now, the best that we... But look that this estimate does not increase the regularity in space, does not increase the regularity in time, but increases the regularity with respect to the expectation, which is something that we really wanted to obtain.
Okay.
So for us, it was good.
Okay, thank you very much. So I have to leave. So there's Jefferson Prada that wants to formulate a question. Please, Juan, you take my role, please.
Thank you. Thank you, Victor, for the presentation. I have a question with respect to the filtrations. Yeah.
Yes.
You consider difference or a family of filtrations depend as time t, no? What happens if you consider different value of t in every filtrations?
Okay. No, how to say? The filtration, where it is, let me see. The filtration quantifies or gathers, as I say, the information of the generated by this Brownian motion until time t. You can consider any time t, okay? And this will give you the information obtained by the experiments, by the evolution of this evolution of the Brownian motion for any time. So how do this relate to the problem? It relates in many senses. Actually, for instance, here, you can see. Here, I'm interested that this final datum is measurable with respect to the final time t, because it is at the point where it makes sense to be evaluated, okay? This should be measurable until, or with respect to the information that I have until the time t, okay? So what happens if you consider some t that it is not exactly this time t, well, I don't know how this random variable is measurable with respect to this filtration, okay? So, for instance, this f, I didn't wrote it at any point. For instance, this f means that f should be measurable with respect to the full filtration, with that all the evolution described for all t's between 0 and capital time T. So the filtration somehow controls all of this information, how it is gathered and how it is studied from the evolution, or from the perspective of the evolution of the random noises. Okay. So I don't know if I understood exactly your question, but I think evaluating at different time t, it will give you the information that you need until that time. You don't know anything from the future, just from the past.
Thank you, Victor. Thank you.
Hello? I have a
Yes.
question.
Yes.
First, a curiosity. In the optimal control theory, this is related to some backward equation. There is in general, there is a forward and backward.
Yes.
That is one curiosity, and the other is the coefficient z or z is related to some diffusion coefficient, as in diffusion theory. Thanks.
Okay. Let me go back to the ordinary differential equation. What is the simplest one? Maybe this one. Okay. And to answer your first question, the answer is yes. This is if you follow the classical, I don't know, the classical Pontryagin principle from optimal control, and you translate it into the stochastic case, you will end up for sure in the same framework that Bismuth developed in the 70s, where he used these kind of equations to describe adjoint variables. So it is exactly the same theory that appears in optimal control appears here. The forward and backward cases transform into a forward stochastic differential equation and a backward stochastic differential equation. So yes, you can think directly for this as the adjoint variable in a control problem. So it is exactly the same notion or the same intuition, all right? And secondly, this process C does not model a diffusion in the classical sense of these stochastic differential equations, or from the PD perspective. What this makes is that it appears here, it compensates this lack of adaptability, or it gives adaptability. Actually, that's the correct sense. It gives measurability of this random variable with respect to what is happening with the filtration. So the noise is not an external noise that modifies or perturbs the evolution of the equation, but instead gives some adaptability, some measurability of the random variable with respect to the filtration. So it is a noise generated by itself and due to this adaptability and measurability of the stochastic processes that are involved. Okay. In one word, for forward equations, the noise is external. For backward equation, the noise is internal and is generated by itself. Okay.
Okay. Thank you. Thank you.
Any question or commentary? Any question? Well, if no more question, thank you very much, Professor Victor Hernandez, for su excelente talk.